Hey, welcome to Math372 Complex Analysis Lecture 10-ish. Sounds good. All right, so what we're going to do today is talk about singularities. So we talked about the definitions of the three types last time, and they were removable, pole, and essential. And as you go down the list, the singularity becomes more severe, the behavior becomes wilder. The definition of essential singularity is anything that's a singularity that's not one of the other two. That's a nice one. Removable, as the name implies, is not so bad. So that was the z minus 1 over z squared minus 1. We could just pull out the z minus 1 and it's not so difficult. The challenge is to come up with good descriptions of behaviors of complex functions. And so whenever things blow up, interesting things can happen. And so essential singularities, we will see phenomenal behavior. I actually forgot, when I was writing down what we were going to do today, I forgot to mention Riemann because I'm just so used to doing Cauchy and not having Riemann in play. It is nice to finally get a theorem due to Riemann. So this is Riemann's theorem on removable singularities. So we basically want a nice condition that will tell us when the singularity can just be removed. Now, one condition we could have is, let's say the function is, continuous and has accepted that one point, and that the limit exists as you approach that point. Then we can just define it to be that, and we're done. That's an extremely strong condition to put in. You want to have the weakest possible condition that you can work with and still get the result you want, so that it will be useful in a variety of settings. So the result is the following. So let's say f is holomorphic on an open omega save at some point z0. And f is bounded. Then if there exists a singularity at z0, it is removable. All right, so basically what we're saying is, except at one point, everything is fine, everything is holomorphic. So imagine we have something like this. Here's our omega, here's our point z0 where bad behavior could happen. And the proof is going to be as follows. We're going to choose some other point z, and we'll take some curve bounding them. We'll often take this to be a disk, but maybe we don't necessarily know it's going to be a disk. Eventually, we're going to take the limit as z approaches z0 and see what happens. But at every finite moment, there will be a separation between z and z0. Okay? Why do we want to do this? We have formulas that allow us to express values at points in terms of integrals elsewhere, in terms of integrals along boundaries. And the idea is we'll express the function at z where everything is nice, and then take the limit as z goes to z0. So we're going to do the standard slit argument where we will come in like this and go around, come in like this, and go around. And so if we call this whole outside thing gamma, let's call this maybe gamma O for outside, gamma z, and gamma z0. As the thickness goes to 0, those two pieces cancel. The integral over all three of these things is going to be 0. So we have 1 over 2 pi I, the integral over gamma 0. Now, which way do we integrate along gamma z? Clockwise. So we've got to be careful. So plus the integral. So I'm going to write it as like minus gamma z to just denote that I'm doing it as a clockwise integral. And then gamma z0 is also going to be a clockwise integral. And then the question is, what function do we want to look at? So a good function is f of zeta over zeta minus z d zeta. And the reason is we know that this function is going to just f of z when I integrate it along this point. And then as we take the limit as z goes to z naught, that will get us hopefully f of z naught. So the idea is we need to somehow get the value of f of z naught. We have an integral formula that gives us the value of f of z in terms of an integral. Is this function nice? Is this function holomorphic? Yes, because the only place it blows up is at the point z naught. And where else? At z. And we've specifically made sure neither z nor z naught is inside our big curve. So what does this integral equal? So it has to be 0. So when in doubt, if you have an integral in complex analysis, guess it's 0. If it's not 0, guess some multiple of pi. One of those two should do it. And of course, since 0 is a multiple of pi, we're OK. All right, so we have 3 integrals now. The integral over gamma of z is just going to become f of z. What is the integral over gamma of z naught going to become? So we want to integrate over gamma of z naught of f of zeta over zeta minus z. And this is d zeta. So we have our circles here. Because z is not equal to z naught, I can choose the radii of these so small that these circles are separated. Because they're separated, zeta minus z is going to be a fixed distance. It's going to be at least a fixed distance. I'm going to have the radii of these circles shrink. As they shrink, this distance is actually going to increase, which is going to make the integrand get smaller. So do we all agree that as the radii of the circles decrease, so as the radii go down, the absolute value of zeta minus z goes up? Your worst case is going to be these 2 points over here, and they're going to get further and further and further away. So 1 over the denominator is bounded. What about the numerator? It's bounded, right? We're assuming a function is holomorphic everywhere and bounded at this point. So the numerator is bounded, so the integrand is bounded. And this is where we use that condition. So the absolute value of f of zeta over zeta minus z is bounded. So if this is bounded, as I shrink the radii to 0, this integral is going to be less than or equal to 2 pi times the perimeter. So if this is a circle of radius epsilon, in absolute value, this will be less than or equal to epsilon times some bounded number. So this is going to go to 0. Okay? So because the function is bounded, the integrand is bounded, the integral then is just going to be perimeter times the bound, which is going to go to 0. Okay, so we now know this piece goes to 0, and this piece is going to go to f of z. So when we just collect everything, we now get that 1 over 2 pi I, the integral over our outside thing, gamma naught, we can actually call that as a closed integral, of f of zeta over zeta minus z d zeta is f of z. Does this integrand make sense for all values? Yes?
Does there need to be a minus sign on one side of that equation?
No, because we had the integral over negative, over oppositely oriented. And so then we move it over to the other side, and the minus sign is. Does this integrand always make sense? We're integrating over the boundary, which is far away from z naught. So this makes perfect sense. As I vary z, is this going to change continuously?
You can't push it close to 0, right?
So we've got to be careful. I can't push zeta close to z0. Zeta is far from z0. So what's going on here is, here's z0, here's z, here's the curve gamma naught on the outside. Zeta lives on the boundary of the curve. So because zeta lives on the boundary of the curve, it's not close to z0. So this integrand is fine. Everything is well behaved. This is going to be a nice continuous function of z. If I change z by z plus h, it's not going to be a problem at all. And now we can take the limit as z approaches z0. And then we get f of z0 is 1 over 2 pi I integral over gamma naught of f of zeta over zeta minus z0. Which, if you think about it, is exactly how you would expect to define f of z0. It's equal to the integral over boundary. Complex analysis, you start on a boundary and you fill inward. Yes?
Over there we assume that zeta minus z is bounded, right? But when we let
Zeta minus z is bounded because here's the point z, and here zeta is on a circle of radius epsilon about z0.
Right, but when we let z go to z0,
Mm-hmm.
that distance shrinks, right?
Yes, but for any fixed choice of z, I'm fixing a z at this moment. I do this calculation for fixed z, and I let epsilon shrink. And I establish this identity for a fixed value of z. Now I let z change to z0. So it's very careful how you approach things. So I fix a z, and then I set my epsilons to 0, I get this result. Then I move z inward a little bit, and then I choose new epsilons, and I do it again. And so for each choice of z, I can find epsilons to make this work. And then I can just take things in the limit. So this gives you a way to remove a singularity. And so in some sense, it can't be that bad of a singularity if the function is defined and bounded. Right? When you think of a pole, when you think of something, you think of it exploding. We're telling you it doesn't explode. Well, if it doesn't explode, it's really not that bad. Think of it as the z minus 1 over z squared minus 1. We can just pull something out. Okay. So Riemann is finally on the board. We had him with the Cauchy-Riemann equations, but this is a real one. So it looks like only half the lights are on. And still only half the lights are. Oh well, okay. All right. So the next part is the Casorati-Weierstrass theorem. And this is to try to describe what happens if you have an essential singularity. So, a pole, basically, pole just means you have like a 1 over z to the n for some finite n. The essential singularity, you should really be thinking of it as it's like going all the way to n going to negative infinity. So let's do an example first. Let's take the function e to the 1 over z. Okay? So the issue is z equals 0. And you might try to say, well, maybe f of z is the sum n goes from 0 to infinity of 1 over n factorial 1 over z to the n. And so this would almost look like a pole of infinite order. Let's try to look and see what's happening to this function near z equals 0. Let's see what values are attained. Let's solve f of z equals w for various w. Are there any w's that you think it's going to be hard to find a z such that f of z equals w? Okay. It turns out that is the only w that doesn't have a solution. And when I say it doesn't have a solution, I'm not saying, well, there's some z somewhere in the complex plane such that f of z equals w. Give me whatever epsilon you want. Give me whatever small neighborhood you want of the origin. And there will be a solution to f of z equals w in that small neighborhood. This is truly remarkable. So not only do you have a solution, you have infinitely many solutions. So let's try to solve something. So let's try to solve e to the 1 over z equals w. Let's write w as r e to the I theta. And let's write z as x plus iy. So 1 over z is 1 over x plus iy. What should we do to 1 over x plus iy? Yeah, multiply by the conjugate. X minus iy, and we get 1 over z is x minus iy over x squared plus y squared. So we're doing some more of the algebraic simplifications we talked about. I talked to my son's 5th grade teacher and said, my students are actually using some of this algebra stuff now in our complex analysis. And she was pleased to hear that it is actually used at some point. So let's try to solve this. So e to the 1 over z equals w. So if we look at the real part, that'll be e to the x over x squared plus y squared equals r, and the imaginary part is e to the I y over x squared plus y squared equals r e to the I theta.
There should be a minus sign.
Probably, yes. Thank you. I'm going to write r is e to the capital R. Am I allowed to do a change like this? Yeah. Because if I do that, it's going to make it much easier to match the real part and the real part. I'm sorry, the magnitude and the magnitude. And not match the angle and the angle. So then I would get, if I use this, I want this to equal e to the r. So I want x over x squared plus y squared equals r. And now what do I want for this part? I want y over x squared plus y squared equal or negative. What does that have to equal?
Theta. Theta plus. Oh, yeah.
Theta plus 2 pi n. We have infinitely many choices of theta that will work. Right? So now how would I solve this? And what do you think happens as n gets larger? What do you think that does to the x's and the y's? So the question is, what's the best way to solve something like this? There's a lot of different ways to do this algebra. We're now back to an algebra game. Now, you might remember this from like Lagrange multipliers. There's lots of ways you can go.
Could I ask you?
Sure.
Like when looking at this problem, like how you decide to convert it to?
Oh, it's e to the r? Well, because otherwise I'd have to be doing logarithms. I mean, I could do it that way, but I want e to the x over x squared plus y squared to equal little r. So that means x over x squared plus y squared would be the natural log of r. Just, yeah, I can do that, but it's just a little bit cleaner to just write equals r. It makes absolutely no difference. I'm just trying to keep the algebra as simple as possible. Yep. So there's a couple of ways you can do this. Anybody have any thoughts as to how to attack the algebra?
Do we want to replace the x squared plus y squared with the x over r?
So you could do x over r. So we could take like ratios of these. And if we take ratios of these, because x squared plus y squared is not going to be 0, we would have to be maybe careful, what if y equals 0? But if we take a ratio, we could get like negative x over y is theta plus 2 pi n over r, and then we could solve for one in terms of the other and plug it in. We could also square each. Then we would have x squared, we would have y squared, x squared plus y squared squared. So then when we add them together, you would have 1 over x squared plus y squared. So we could actually get 1 over x squared plus y squared would be r squared plus theta plus 2 pi n squared. So just square this, and add. That's nice because that now tells us the size of x squared plus y squared. So we now get x squared plus y squared is 1 over r squared plus theta plus 2 pi n squared. So as n gets very, very large, x squared plus y squared is getting very, very small. Good, right? We're trying to find a point near the origin. Whenever you're doing algebra, always stop and ask, is this answer reasonable? And as n gets larger and larger and larger, the sequence of points is getting closer and closer and closer. If we wanted to, we could actually put subscripts n on these to tell us that this is the nth point that will work. Well, now that we know x squared plus y squared, now it's really easy to get x. X will just be r over r squared plus theta plus 2 pi n squared. Well, that's a terrible 2. Terrible 2's. And then y would equal theta plus 2 pi n over r squared plus theta plus 2 pi n squared. And if you want, I'll put on the subscript n's over here. We now have a sequence of points, and you can see as n gets larger and larger and larger, these points are converging to the origin. Even though this has an n squared down below. There probably should be a negative. Yes. Thank you. So we can solve infinitely often e to the 1 over z equals w as long as w is not 0. Is there any way to define this function at the origin? How should we define this function at the origin? Well, the fact that we've just shown what we've shown should make it clear that we're screwed. If it wasn't being recorded, and my kids might be watching this someday, I would use stronger language. Why are we screwed? Why is it so bad? Why is there no way to define this at the origin?
You don't have background, so you couldn't, when you tried to integrate.
So, but what that just means is we can't use Riemann's method. There might be, it's good to know that we can't use Riemann's method, but maybe there's another way we could attack the problem. I claim we are fundamentally screwed. It's so hard to just keep it to that, near the origin. What values do you see as you get arbitrarily close to the origin? Every single value. This is the giant pick me. Every non-zero number in the complex plane is begging you choose it as the value of the function at the origin. And every point other than 0 has a legitimate case. For every point, we can find a sequence approaching the origin where the function takes on that value. So you fix an omega not equal to 0, I can construct a Zn of omega, which will be a xn omega plus I yn omega, such that e to the 1 over Zn of omega equals omega, and Zn omega goes to 0 as n goes to infinity. So no matter what value you choose in the complex plane, I have a sequence of where I'm always taking on that value. So the only possible definition for the value of this function at the origin is every single point, save the origin. So there's no way we can extend the definition. Now, there's an amazing result, it's Picard's theorem, that says if you have a complex valued function that omits 2 values, it must be constant. So Picard, let's say f is entire and f omits at least 2 points. then f is constant. That's an amazing result. Is there anything like this in real analysis? If you have a real function that omits 2 points, yeah, that's not telling you that much, right? And the function could be infinitely differentiable as well, for the real analysis case. What if the function omits just 1 point? Can you give me an example of a function that is entire and omits just 1 point? 1 over z is not entire everywhere. E to the z. So consider e to the z. It omits only 0. So we've talked about elephant gun proofs or tactical nuclear proofs, just really throwing the kitchen sink at a problem. I want to prove that I can solve e to the z equals w for any w other than 0. I know e to the z is never 0. By Picard's theorem, if it omits 2 points, it's constant. Since e to the z is not constant, then this is the tactical strike. Okay? There are better ways to find a solution to e to the z equals w, but if you just want to prove existence, here is probably the most overkill existence proof possible. Okay? It's sometimes nice to just use the results you've proven and just blow a problem to smithereens. Now, of course, that means you have to prove Picard's theorem, which is a big result. So it's a bit of work to prove that if you omit 2 points, you're constant. We will prove something a little bit weaker. We will prove that if you have an essential singularity, then you are dense in the neighborhood of that singularity. Something stronger is true, but we're going to just prove just that. So over here, for instance, much more was true. It's more than just we are dense. So dense just means you give me any point and you give me a distance, I can get within that distance. We've shown here you actually hit it. And you hit it infinitely many times, getting closer and closer and closer. All right. So if you continue in complex analysis, you will see Weierstrass's name somewhat frequently. He has a lot of very nice results. He might have been a school teacher when he proved this. So this is Casorati-Weierstrass. If f has an essential singularity at z0, then f is dense at z0. Okay. So this just tells you that wild things happen near an essential singularity. And you should think of the e to the 1 over z as your go-to example of what's happening at an essential singularity. All right. Proof. Assume not. So let's assume it's not dense. So what would it mean if it's not dense?
So dense means that it takes any value arbitrarily close to z0.
So dense is always relative to a certain set. I'm saying this is dense in the complex numbers. That you give me any complex numbers and you give me any epsilon, then there will be a z such that f of z is within epsilon of your complex number. That's what it means to be dense. So what would it mean to not be dense?
Given any point you can't get within epsilon?
No.
Given a single point, you can't get within.
No. You have to phrase it very carefully. Do you know the joke about Scottish sheep? An engineer, a physicist, and a mathematician are on a train in the Scottish countryside, and they see a black sheep. And the engineer goes, "Wow, I didn't realize Scottish sheep are black." And the physicist goes, "No, no, 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 no. You're concluding too much. All we can conclude is that this Scottish sheep is black." And the mathematician goes, "Oh, all we can conclude is there exists at least one sheep in Scotland which is black on at least one side." You've got to be very, very careful. When I say it's not dense, what that means is there exists a W in C. We don't know which one it is. It's not necessarily the case for all of them. There could be a lot of W where it's dense, but there's got to be at least one point where it's not dense. So not. There exists a W in C, and there exists a delta greater than 0 such that for all Z in C minus Z naught, f of Z minus W is greater than delta. Oh, we can even do greater than or equal to W. Doesn't matter. That's what it means not to be dense. There's got to be at least one point where when I apply f, I am at least delta away from that. Okay? We all happy with what it means to not be dense? Okay, so now let's consider the function g of z is 1 over f of z minus w. Normally you'd be afraid. Why would you be afraid to write this down? Yeah, f of z could equal w. But we're assuming that it's not dense. So since we're assuming it's not dense, we're fine. So what do we know about the absolute value of g of z? It's less than or equal to 1 over delta. So g is bounded. What does it mean for g to be bounded? Or what can we do if g is bounded? So if there's a singularity, the singularity is removable. Okay? So it's extremely important that we get to this, in today's class, so you can actually see why we care about Riemann's removable singularity theorem. This is actually a condition that can arise. So the real issue is what's going on at z naught. Well, we've just shown that the function g is bounded. It's fine everywhere except at z naught. By Riemann's theorem, g has removable singularity. By Riemann, g has a removable singularity at z naught since it's bounded. So what we would like to then say is consider now f of z is going to be 1 over g of z plus w. I'd love to use this now as my definition of f by just, oh, did I do it wrong? I think I did it wrong. It would be f of z minus w equals 1 over g of z. So f of z would equal to 1 over g of z, plus w. Did the algebra wrong. Can we do this? Am I allowed to do this? Well, if you want, say, f of z naught is 1 over g of z naught plus w. If that maybe makes you a little bit more scared. what do we need to know if we're going to do something like this? So what's dangerous in this line here? Yeah, g of z could be 0. Right? If g of z is 0, I'm dividing by 0. Yes?
Can g of z ever be 0 if it's defined with a 1 in the numerator?
But we're taking the limit as z goes to z naught. So for instance, let's say f of z naught is plus infinity. Then g of z could be 0. But we know g is holomorphic. And so because g is holomorphic, g has to have either a 0 or finite order. And so you would get a polar finite order. So it's possible that maybe you have, g of z is 8 z minus z naught to the 9. And then 1 over g of z would blow up. But g has to have a finite degree 0, a 0 finite order. So this would then give f has a pole, not an essential singularity. As the order of g at z naught is finite, yields worst case f has a pole of finite order. Contradiction or contradicts the essential singularity. Right. We're not going to really do much more with stuff like this. It's worth seeing the types of behavior you can get at strange places. It's worth seeing the types of singularities. For the most part, we're not going to do much with essential singularities. For the most part, we're not going to have to worry about removing singularities. You should be aware of the existence of stuff like this. You should be aware of the existence of Picard's theorem. That we have this incredible classification of functions omitting 2 points. That is extremely well understood. Okay, and then over here, the behavior near an essential singularity is just incredibly wild.
How do you know as you're taking the limit that the order is still finite?
Well, because by Riemann, G is holomorphic. It's a removable singularity. So because of that, now G is a holomorphic function. So it's either it doesn't have a 0, or if it has a 0, the 0 has to be a finite order. Unless the only other possibility is, could G be identically 0? So we should probably explicitly state, can G be identically 0? Well,
how do you know from Riemann that it's holomorphic? Don't you need to assume that it's...
we know that f is fine except at the point z naught. And so this function g is holomorphic and has a removable singularity. So we can now make g a nice holomorphic function.
Right.
And because it's holomorphic, it doesn't have a pole. It has at most a 0 finite order.
Right.
If it had a 0 of infinite order, g would be identically 0. Well, g can't be identically 0 because there is some variation here. F of z does change. So g can't be identically 0. So since it can't be identically 0, the only case that's left is g could have a 0 of, say, maybe degree 8 or 9, whatever, degree 9 at z naught. Well, then this would give that f has a pole of order 9 at z naught. But we're assuming our function f does not have a pole. We're assuming it has an essential singularity. And that's now a contradiction. So if you have an essential singularity, you are dense in a neighborhood of the essential singularity. And this is what we saw with the e to the 1 over z, that when we're trying to solve things, we don't have to look very far. We can look in an arbitrarily small neighborhood. Okay, so we've now removed singularities, which is great. We've done Casorati-Weierstrass, which is great. We've looked at examples. Okay, And so now we've talked a little bit before about compactifying the complex plane. The stereographic projection, we're not going to do too much with that. The book has a section on it where you can basically look at all the points that are getting further and further and further away from the origin are essentially mapped to the top of the sphere, the North Pole. And this is often called the one-point compactification of the plane. And it gives you an idea of what it means to be going off to infinity. That in some sense, all that really matters is that your magnitude is going towards infinity. The direction doesn't matter. The directions are all the same. Another way of looking at this a little bit more rigorously is that we can change variables. Let's let w equal 1 over z. And so if we change variables like that, we basically map everything very far from the origin to something very close to the origin. So here's z, and let's let that be 1 over w. So if you think about the absolute value of z greater than or equal to r, that gets mapped to the absolute value of w is less than or equal to 1 over r. So the points that get further and further and further away from the origin, these are the points that are going off to infinity. If I do this inversion, then in this, all of a sudden I'm now looking at what's going on very, very close to the origin. So the whole point of this is to just adjust the notation. We often don't want to use infinity as a symbol and be working at the point infinity. So we're essentially mapping the point infinity to the point 0. In some sense, in a deeper sense, what's going on is we love compact sets. And the complex plane is just one point away from being a nice compact set. It seems a little surprising, given that it has infinite area and it's going off to infinity. Normally when you think of compact, you think of things that are bounded, right? Going off to infinity seems a little bit unbounded. But we have this beautiful map where we basically kind of fold some of it down and some of it up, and we get almost the sphere except for that one little point. And so what's really going on is a lot of times we talk about maps on the extended complex plane, where we include the point infinity. And you now allow infinity as an output. And so if we have the function e to the 1 over z, or the function 1 over z maps the point 0 to infinity. And what does it map the point infinity to? Maps infinity to 0. You've got to be extremely careful with infinities. Can you add two infinities? If they have the same sign. So we've got a few minutes left. So infinity plus infinity is infinity. Infinity minus infinity, yeah, big question mark. Look at the limit of n squared minus n or n squared minus n cubed. We can't do that. All right. Infinity divided by 0. Infinity. We have to maybe worry a little bit about, is it positive 0, negative 0? So we'll say coming from the positive side. So that's infinity. Infinity times 0. The weights matter. So I'm going to prove to you, actually, that infinity times 0 can sometimes be negative 1 in a very nice geometric way. And since this is complex analysis, you can actually make this proof rigorous. Let's go back to high school algebra. All right? I give you two lines that are perpendicular. And they have slopes m1 and m2. Who remembers what the product of the slopes are? Negative 1. Excellent. So a really good way to prove this is with complex analysis. You could call this point e to the I theta. Move over here, e to the I, maybe theta plus phi. Write down, find everything. So it's a nice exercise. Prove this. Prove that the product of the slopes is negative 1. Okay? So the product of the slopes is negative 1. Does anybody have a pen I can borrow for a moment? Thank you. All right. So I've got two pens. I only brought one pen by mistake. So does everyone agree that the product of their slopes is negative 1? Still negative 1? still negative 1, still negative 1, still negative 1, it's still negative 1. What's it right here? What's the product of the slopes? It's infinity times 0. What's infinity times 0? Well, if I move over just a small little bit, it's negative 1. If I move back a little bit, it's negative 1. How would you define it right here? Depending on the problem, you will define things such as infinity times 0 in different ways. This kind of feels like a removable singularity. When I'm looking at what's going on. Negative 1, 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 negative 1. Let's define it to be negative 1 right there. And as a nice exercise, prove this, write down what would be the equation of the slopes. You can see some trig coming in. Find, what's the best way to prove something like that. So we do have situations where these removable singularities come into play. And there are very natural ways to define things. So I would define the product of the y-axis and the x-axis to be negative 1. I think that's the correct definition in this case. We still have 2 more minutes left. So with 2 more minutes left, let's talk about 1 or 2 other things. What's 3 factorial? 6. So this is 3 times 2 times 1. What's the interpretation of 3 factorial?
The number of distinct ways to arrange.
Good, the number of distinct ways to arrange 3 objects. What's 0 factorial? 1. What's the interpretation?
Number of ways to arrange no objects.
So you're saying there's one way to arrange no objects.
Do nothing.
There's one way to do nothing. Because I could do nothing this way or I could do nothing. No, there's one way to do nothing. So are we willing to accept 0 factorial equals 1? It's extremely useful for definitions, for all the things we're looking at. Now it turns out that negative 1/2 factorial is the square root of pi. Have we talked about that? That's the value of the gamma function. So what I want to end with is, what do you think 0 to the 0 is? And does it depend on the problem you're looking at? Does it depend how you're approaching 0? How would you define 0 to the 0? 1 is definitely a natural candidate. What else is a natural candidate? 0. So depending on the situation you're in, you could easily be in a situation where 0 to the 0 is 0, where 0 to the 0 is 1, and a lot of it's going to come down to the story you're telling, to what you're looking at. Okay.